You should start taking notes. Your exam is coming up soon on basic cell structures, and we're going to make sure we know our cell structures and differences between cells. It's one of the major objectives in this unit. So there's really two objectives in this unit. The first is to understand the cell and all its different structures. And function. And that's the title of the chapter, Chapter 7, which you should have read already. You were asked to read and make index cards, or those foldables. I sent you a video on how to make the foldables. Could anyone who's done, I see a lot of people have, could you show everyone what you've done? Hold them up. If you've done it, hold it up. So here we have examples. There should be a number of these. It shouldn't just be one or two. There you go. Look back here. Look how many she has. All right. Cutting them all the way on cutting both slips of paper is going to be an issue for you in the long run. And you can see Frank has a lot as well. Because you all did the vocabulary from the video and you did the Chapter 7 vocabulary, the important words that you thought you were going to have trouble remembering. So at this point, you should, when we start to discuss this, because you read it, because you've made index cards, it should be evident that this is what is important and what is not important. When you see some word that you have on your foldable, when you see some word that you remember from the chapter reading, you should put an extra asterisk on it, highlight it, do something, make a note that this is probably going to be something that's going to be tested. So the second thing is, and it's really just a subunit of structure and functions, is how do things move in and out of a cell. So those are two major objectives, and there's a lot to learn in order to understand these two major, well, let's call them goals. Big, broad goals. These are our goal at the end of the unit. Your goal is to make sure you understand these two things. How do things move in and out of the cell, and all the different structures and functions of all the different cell types. And if you know these two, it's going to be about 14% of your Ohio State test. It's going to be a good portion of any question you get that's science-based on a standardized exam is going to be based a lot on these ideas. So let's move on. We've talked a lot about these things. Anybody tell me what they are? What is this representing? At this point, everyone should be automatically saying, without looking up, phosphate and fatty acid. Let me use a different color. Two of them, 1, 2. To make a phospholipid. That is a phospholipid. It's the basis of a cell membrane. It's the first structure that had to form for life on Earth to start. Via a bunch of different experiments, already did a very interesting experiment early on that we talked about, but during various experiments, we know that these phospholipids had to come first with a hydrophilic head and a hydrophobic tail. It had to have this for the following reason. If you have a bunch of water molecules in a solution yeah. Yeah, that's just water. You can draw water. If you can't draw water, you guys need to start drawing it a little. You guys have to start practicing a little bit. But this is, you have to keep up. It's H2O, water. And you have a bunch of them now. You have to consider that there's probably billions of these in a glass of water. It's just all hanging out with each other, and they're always moving. They're always moving. You know that from middle school, that things are always moving. Things have kinetic energy. Do you remember kinetic energy? Yes? Yes or no? Yes or no would be helpful. Yes, okay. Thank you. So, kinetic energy, as you remember from middle school, is equal to 1/2 mv squared, where v is movement. Here, this is mass. You know that each of these atoms have atomic mass. They're all moving all the time. Even when something's sitting still, you think that that table is not moving. It's moving. It's vibrating. They're really tiny vibrations, but they're vibrating. Right now, you're going thousands of miles an hour. Over 1,000 miles an hour, you're moving at this second. Every second, every day on planet Earth. You go around the planet one time every day, don't you? You move around this whole planet one time every day. Correct? Yes or no? I'm seeing confusion in your eyes. Do you not move around this planet one time every day? Yes or no? Why do you say yes? Why do you say yes? Because why? Why are you moving around this planet once a day? Why? I'm asking you because the answer is simple. I'm not asking you because it's difficult, or it shouldn't take you that much thought. Think. Why are you moving around? Did you find them all? You took everything out of the whole cabinet.
Yes.
All these books out of that whole cabinet. There's only 2 of them in there.
Yes.
There's something wrong.
Most of them were Unit 4.
Yeah, I got you. Put it back. I'm sure that there's more in there, but I'm gonna come back to it. Yeah, the unopened ones.
I didn't know you wanted us to do that.
Yeah, the unopened ones. They're unopened. Not the open one. I knew there were more in there. Ladies and gentlemen, does this planet not turn on its axes? Yes or no? How long does it take to turn on its axes? People, you're not. It's too early in the morning not to be tired. 5 days. It takes 5 days for the Earth to turn around. What do you mean it doesn't make sense? Yeah, it's not too early. You just want. I said it's too early for you to be tired. It's not too early for you to be awake. It can be both. Think. The Earth is turning around. How long does it take for it to turn around? 5 days. Thank you for guessing. I appreciate it. It's not 5 days. 5 days is wrong.
That's all she just said. 365 days.
It's not 365 days. It's 24 hours. 1 day. One day to turn around its axes. That's what we call a day. When the sun rises, the sun's not moving, we're moving towards it. Is that clear to everyone?
That's very much clear.
No? Okay, I'm asking. I can't hear you. You guys are mumbling. So we're turning on its axis 24 hours, one day. When you see the sunrise, it's because you see the sun in the background as you are a dot on the planet, as you see the sun rise, as you move towards it. Is that clear to you? That should have been taught to you in middle school. I'm sure it was. You may not remember it, but I'm sure it was. Then every 364 and a quarter days, this planet moves around the sun. So it's revolving, spinning on its axis, and I'm sorry, yeah, that's right. What's the other one? What's the other word? And it orbits the sun as well. Okay? Huh? There's two words. No, it's for sure it's moving towards the east. So everything's moving from the very planet moving around the sun to the planet spinning, moving 1,000 miles an hour, moving thousands and tens of thousands of miles an hour as it goes around the sun. Everything's moving. No, you're sitting somewhere else today. You're sitting over there. That table, second table, I'm pointing. I'm pointing. That's your permanent seat. I'm pointing. That's it? Yeah, pick a seat. Permanent seat. Thank you. So, everything's moving, including all these water molecules. They're vibrating. Now, this is going to be a very important idea. They're moving in both directions. They're vibrating back and forth constantly. There's no question that they're vibrating. They're turning, they're spinning, they're moving. Nothing's standing still, ever. So, you're going to take, if you place these molecules that have a hydrophilic. What does hydrophilic mean? You read the chapter, you've listened to class, you've taken notes, you made index cards. Hydrophilic, what does it mean? And then another side is hydrophilic and it's hydrophobic. Correct. Somebody remembers. Hydrophilic and hydrophobic. If you don't have this in your notes because you've been coming in late, because you have been absent, because whatever, then get it in your notes. You need it. You need to know it. I'm about to tell you. Again. So this phosphate, remember it's a phosphorus with 4 oxygens, and it's attached to a carbon. One of the oxygens is attached to a carbon down here. There's a negative. Hold on a second. I'm probably going to say yes to you, but hold on a second. Okay. This is phosphate, and phosphate has a charge. And we talked about that last time as a negative charge. And this is a long chain of carbons. This would be a saturated. This is a saturated fatty acid, long chain of carbons, saturated. Meaning no double bonds, correct? Correct? We remember that?
Correct.
And this one here is another long chain of carbons, except this one's going to have a double bond. I decided it's going to have a double bond. And double bonds are shorter, so that means that they're going to they're going to bend. Let me make it a little more exaggerated so you can see it clearer. It's going to bend the fatty acid away. It's going to make the fatty acid kick out. Do you see it? This one's straight, this one kicks out. Do you see that? Because if you don't see that, it's going to be really hard for you to understand what's going to happen in this membrane. Then this hydrophobic and hydrophilic, what does that mean? That means when we look at water, as we discussed before, water is polar because water is that greedy Mendoza that likes to pull on the electrons. And it's going to be that partially negative and partially positive. It's going to have two poles, correct? Yes? Do you see that? Two sides. It's going to have two sides. One side is going to be positive, and one side is going to be negative. So it has a positive and a negative side, and we call these poles. Just like a magnet. So because of that, water is what? Water is polar. Very good. And we remember the rule, or at least we should remember the rule that I told you, make sure you write down and put on the index card because it's so important. Like dissolves like. So polar dissolves polar and ionic. So if they dissolve each other, they love each other. If they dissolve each other, they mix with each other. If they mix with each other, they love each other. The Greek word for love is philic. Phili or something like that. Philic is to be love-like. So if you love someone, you're philic with them. So hydrophilic means what? Water loving. Water loving. Water loving. Hydrophilic means they love water. So the negative side loves water. It's like Romeo and Juliet. Because the negative side loves water. They're in love. They'll mix all day long. They'll dissolve. They'll become one. Like two people getting married. Easily, these two want to get together. But the problem is the phosphate is attached to a water hating, a water fearing. The word for fear in Greek is phobic. You ever hear phobias? Right. And this is hydrophobic. So it's these fatty acids, lipids in general, are hydrophobic. They hate water. They will not mix, can't stand each other. A true Romeo and Juliet situation. Phosphate loves water, and the lipids hate water. What's a phospholipid gonna do? So if you take a bunch of these, and for right now, let's just all make them saturated. You take a bunch of these and you put them in a glass of water, what's gonna happen? Can you guess? This is a guess. This is something you can guess if you think about it, but you may not be able to. You shouldn't be ashamed if you can't. If you get it wrong, you shouldn't be worried about it. I haven't told you yet. What are they going to do if they fall in water?
They're gonna, I would say like lose like their energy.
Well, they have energy. They're not going to lose it. They might transfer it, but they get some back from water because they're going to bump into everything's going to bump into everything else. So you're right on that. Say what now? Yeah. What's going to attract? What part of this is going to attract the water? The hydrophilic. Excellent. So what will happen is, just out of common sense, the The part that loves water is going to mix with water. They love each other. There's nothing you can do about it. The part that hates water is going to stick up out of the water. It's try to stay away, as far away from water as you can. It's like that, like your best friend's boyfriend that you hate. Like you love your best friend, but you can't stand that guy or that girl. She's too messy. So you stay as far away from her as you can, but you still want to be with your girl or your boy or man or woman or whatever. And so the water loving part points to the water hating part away from the water. Does that make sense? That's what happens to phospholipids when you put them in water, and they'll form a thin layer on top of water. But something interesting happens. Give it some time, and under the right conditions, given enough time and the right conditions, these lipids, these phospholipids, will all of a sudden start to do this. They'll mix with each other. They'll make a circle, because like dissolves like. That means the hydrophilic love the hydrophilic. And what do the hydrophobic do? They stay away from hydrophilic, but what do they do with each other? Like dissolves like. What do? They mix. They fall in love. All the lipids love each other. And if they form a sphere, this is cut, okay? So you have to imagine that you're looking at a sphere, a ball, okay? A ball of lipids where the outside is hydrophilic, the outside's hydrophilic, and the inside's hydrophobic. Does that make sense? Why does that make, why do I say that? Because here, this part is water loving, so it points towards the water. Mainly because it has a phosphate, a PO4, as a negative, has this phosphate sitting there as part of that head, and it's pointing out. The long carbon tails are hydrophobic. This is as far away from water as they can get and still be mixing with each other in this center. This is one drawing of it here. This is another drawing of it here cut open. This is called a micelle. Micelle. It's the first structure that probably formed before life started. This is like, if you're looking at a car, this would be like a spark plug or a piece of metal. It's the component that you need to build the organelle. It's like metal before you can build the carburetor, or metal before you can build the engine. Does that make sense? If you can think of it that way. This is what you need if you're going to build a cell. All right. Do we all have this so far? And I believe this is in your chapter. This micelle is not good enough for life. This is not alive. This is what you call detergent. When you put detergent in your washing machine, this is what you form, these micelles. And what happens is any grease that you have, any oils that you have on your clothes, where do they go? Any hydrophobic stuff that's in your clothes, where do they go? Now I expect you to know this. Like dissolves like. If this is what's in your detergent and you have grease on your clothes, where's the grease going to go?
It's gonna go away, it's gonna go in water.
It's not in the water because it hates water. That's why you can't just wash it without soap. It won't get the grease out. Because water won't, grease, oil and water don't mix. They hate each other. Didn't we just say that? Here you have a micelle. This is what happens when you put detergent in water. Where's the grease on your clothes going to go? Look at it. Think on it.
Is it gonna go like what?
What is the grease? Hydrophilic or hydrophobic? Hydrophobic. What did we say? Like dissolves like.
So does the grease dissolve?
Where? With the other hydrophobic in the middle of the micelle. It's going to go right in the middle of the micelle. And it's going to get stuck there because it doesn't want to come out. And then when you hit the spin cycle and the water comes out of all that water comes out of the washing machine, where's the grease? It's going to come out too in the little micelles. Those little bubbles that you see coming out. You ever see that in your washing machine when it dumps the water? Oh well. You guys need to pay more attention. Those are full of the grease and the dirt. The dirt is dissolved by the water if it's hydrophilic. If it's hydrophobic, it's in the middle of the micelle. Do you see it? In the middle of this ball that I cut open here. But that's no good for life. It's no good for life. Because in order to have life, you have this chaotic place with all kinds of crazy things going on. One of the things that you need to do is you need to have order. You cannot have chaos. Chaos is death. Life is order. So that's characteristic of life number one. You must have order in life. Disorder leads to death. So, two, the second major characteristic of life is you have to have compartments. Why do you need houses? For shelter from what? Rain, snow, well, not necessarily disasters, but because of weather, right? If it gets too cold or too hot. So you have to be able to control your environment, correct? Because otherwise it becomes at least uncomfortable and maybe deadly. If I put you outside naked in the frozen snow, what happens to you? Freeze to death. You know, like that show, whatever, Naked on the Island, they put people. It's on ABC. They don't show anybody naked. They just go naked into the woods.
No, I show like they body, but they blur it out.
But they blur things out, huh? No, I don't watch any of that stuff. I don't watch TV at all. I just saw the commercial for it, and I was like, this just...
You know you paid $6.99 for that little episode?
How you know $6.99?
Hey, I'm just guessing.
No, first of all, I don't know how much it costs. I'm glad you do. But no, I'm talking about like that show that's on regular TV. Thank you very much. Naked and Afraid, I think that's what it's called. Yeah, it's crazy. I saw the commercial for it. I don't watch those things. I don't watch the Housewives of New Jersey. I guess they're gonna have a meeting with the New Jersey I heard it on the radio this morning. I'm like, this is outrageous. Not outrageous. Ridiculous. So anyways, the point is you put outside. Why is that a problem? Because we need a consistent environment. We need to control the environment. We need to be warm in the winter and cool in the summer. Otherwise, if it gets too outside of our normal, we die. Death is no good. Yes? We all agree? Yes or no? Thank you. So compartments allow us to regulate that. But having a single hydrophobic center does not give us compartments. It certainly does separate two spaces, doesn't it? There's a space in here that's hydrophobic and a space out here that's outside. So there's an inside and there's an outside. Okay. but it's not as useful as the following. Something else these lipids can do. These are amazing little things, these little lipids. These lipids can form a bilayer. Bilayer. What do we mean by bilayer? Two what? Layers. It really is not difficult. It really is not difficult. Yeah, it's in the book. It's in the book. That's where you remember it. So what they do is, if you have enough phospholipids, and again, they're under the right conditions, what will happen is something amazing. And again, I do not care if you consider it to be completed by an engineer, like a god, or you think it happened by accident. I don't care. The point is, it happened, okay? And what happens in a bilayer is you have two layers of phospholipids. It's still a ball, it's still a sphere, and I shouldn't even call it a sphere or ball, but it's enclosed, it's three-dimensional. I can only draw it in 2 dimensions. Now I'm drawing it, so there's absolutely no reason why you guys can't draw it. In fact, I'm drawing it, and I'm also erasing and redrawing. So that gives you plenty of time to at least start the drawing. It's a bunch of little circles. They're not perfect. They're going around in a circle. I'm doing it right in front of you in real time, not speeding through it. Shouldn't be anyone not following along. Then in the center, the inside, you have water. Outside, that's H2O. Let me make that a little smaller by zooming in. H2O. There's water inside, and there's water outside. So that's where the blue phosphate heads are pointing towards the water, because they love water. What's in between these two sides? Hydrophobic. They don't like water. Now everybody's happy. The hydrophobic side of the phospholipid get to hang out with the hydrophobic sides. The hydrophilic sides get to hang out with the hydrophilic sides. Now everybody's happy. Again, I'm drawing the lipids.
Would they ever want to combine with each other or not?
What do you mean? What do you mean by combine? They. All right. Say that again. Combine in what way? What do you mean? Will the hydrophilic ever mix with the hydrophobic?
No, I'm talking about the water.
Will the water ever mix with the hydrophobic? They will pass through reluctantly. Not easily. So the answer is they don't like each other, but they will, with enough energy, with enough movement. Remember, everything's moving. That's why we call it a fluid. So there's this layer in the center that's hydrophobic. Hates water, fears water. And this side that's hydrophilic. Loves water. All right. Now you have two actual spaces. Can I use the word, what's another word for, what do you call someone when they go to prison, the place where they live, the room where they live, what do they call it?
A cell?
A cell. A cell actually means a room. That's all a cell means, is room. The first person to look under the microscope, as discussed in your chapter, looked in the microscope and saw little rooms, little spaces in a plant cell. And he called that a cell because that's what a room was a cell. So this is a cell. A cell is something that has a single room, at least. A room. Surrounded by remember, this is three-dimensional, correct? I'm drawing it cut out, but please remember, the cell is actually a ball or some shape. It can be all kinds of shapes, but it's three-dimensional. I'm just cutting it. This cell is cut in half. I'm looking at it like cutting an orange, and I'm looking at the face of the orange. Does that make sense? The flat side of the orange. All right. So, what's the problem here? Well, let's think about it. The water has a bunch of stuff that's dissolved in. There's some sodium ion. There's some calcium ion. There's some glucose out here. Glucose is polar and large. By now, you should know that hexagon is glucose, but I'll go ahead and put GLU for glucose. Sodium ion. And I'm going to write the word ion just so I can emphasize to you that that's what these words mean, that they're charged. Ionic, they have a charge. Ion means a charge. It could be more than one, like in this case it's 2, in this case it's 1, but it's a charge. Polar just means it's pulling partially. So these guys love water. They're ionic, they have a charge, or they're polar, they love water. There's other stuff in here. You might have oxygen gas. Oxygen gas is small, so there's 2 rules for dissolving. If they're really small, or they are nonpolar and medium size, all right, then they can go right through the membrane. They don't need any help. They can go right through here. So this little oxygen molecule is nonpolar. We talked about that. I'm not going to go back and talk about it again. But it's nonpolar and it's small, so it literally goes right through the membrane into the cell. CO2, carbon dioxide, goes right through the membrane because it's small and it's nonpolar. So it goes right through the membrane. It goes both ways. It goes in and out both ways without any problem. They're small and nonpolar. But what about sodium? You eat salt. You crave salt. Why? Because you need salt. How do you get the salt into, this is salt, right? Anything charged in a solution is a salt. Remember that. Remember we defined what salt was. A salt is when a non-metal and a metal come together and one takes the electron, the other one gives it, creating 2 ions, one positive, one negative. The examples were sodium chloride, calcium chloride, remember that? Lithium chloride. So you got all these ions in water. They got to get in. How are they getting in? There's no way. These will not pass through this membrane. Sugar is too big. It will not pass through the membrane. It's not 2 atoms. It's 6 carbons, 12 hydrogens, and 6 oxygens. So it is not going through this membrane easily. What do you need? Wait a second. Read the question. I didn't write the question down. Oh, repeat, yeah. How are you going to get other things that you need to get into the cell, like sodium and calcium and sugar, into the cell, if this is nonpolar and these will not pass because they're big, because sugar is big, and these are charged. They're not passing through the membrane easily. So how do you get them through? How are you going to get them through the membrane?
Well, less like hydrophobic and hydrophobic.
I like your idea. If I put you in a room, now instead of putting you out in the cold, now I put you in a room with 6 walls, 6, a floor, a ceiling, and 4 walls. I put you in. How you get now? A ceiling, a floor, and 4 walls, made of brick, all made of brick. How you get out?
If you don't have no like tools, you're not getting out.
Oh, what do you need to get out?
Like
A door or a window is correct. No, I like your hammer idea. You're right. You would need a hammer to get out if you were locked in some kind of. It would be a crypt at that point, right? It's not really a room that we would talk about. So you need to put a hole in this. You need to put a door. What life does is it uses a protein. Uses those amino acids that we talked about and creates a big old molecule, big chain. A big chain. Why does it? Oh, I see. Okay, well, whatever. Makes a big chain of proteins. And the interesting thing about proteins is it has a bunch of different R groups. So some of the R groups can be non-polar. I'm just going to put little blocks for the amino acids. Some of the R groups can be non-polar. They fold like you're foldable. And some can be polar. And they're all linked and they all fold into each other. Again, this is 3-dimensional. And what am I creating when I do this? A door, a way in. All right, we're going to continue this tomorrow, but please make sure you look at this and see what I just drew. Please make sure you understand this because this is a big thing that's tested everywhere.